Okay, let's go ahead and finish out chapter 3.8 with a short video here first. Remember that we left off when we were talking about this extension to Simpson lines. It said that if we have U and V as points on the circumcircle of triangle ABC, then the angle between the Simpson lines, having these points as poles, is equal in degrees to half the arc UV. We worked through the proof, and basically the idea is that if we pick the points U and V, then choose a side of the triangle and construct the perpendiculars. We can then identify 2 points, I guess, that are on the Simpson line. So where U intersects BC, or this point drawn in right here, is on the Simpson line. So also where U intersects where the foot of, I guess, V on line BC, that point right there would be on the Simpson line. It also should be pretty apparent that those 2 lines are going to be parallel because they're both perpendicular to BC. But the way this gets proved is that we appeal to theorem 3.1. If we call SL parentheses P the Simpson line with pole P, then SLU is parallel to AR and SLV is parallel to AS by theorem 3.1. That was the first theorem we proved. And it's pretty easy to see that RAS, the angle RAS, is equal to the arc RS, right? So that's this arc right here will be related to that angle right there by a factor of 1/2. And, you know, since UV, UR is parallel to VS, we can say that the angle between SLU and SLV must also be half of RS, which is equal to half of UV as well. And the idea there is that RS and UV share exactly the same arc on the circle. So the two, and that's due to the fact that UR and VS are parallel. We spent the last part of the period on Friday kind of trying to decide why that was just obvious without any proof given in the text. And we convinced ourselves, I think. So this is a nice one to do in GeoGebra, so I thought I would do it really quick. So if we go into GeoGebra and, let's go ahead and select all here. And just delete. What we'll start with is a triangle, of course. We'll construct the circle through 3 points here. We'll put a point on that circle. And then what we'll do is we'll go ahead and construct the Simpson line. So to do that, what we need is we need the side lines. Once we have the side lines, we can construct the foot of the perpendiculars. So I guess we would have a perpendicular line through here, perpendicular line through here, a perpendicular, oops, got the same one twice, perpendicular, perpendicular through there. Okay, looks like we can then construct the intersections of these 2. Let's see, the intersections of these 2 and the intersection of these 2. Lots going on here in the drawing when you do this. So it's nice to get rid of a few things. I think that's our Simpson line then. Let's go ahead and color everything up so that we can kind of keep track of the 2 lines we're going to construct. So this one I'm going to call red. Maybe. Oh, I see. So this one red. This one red. This one red. And this one red. Okay, so we should have a Simpson line whose 3 feet of perpendiculars sort of follow around in a collinear fashion. This is the thing we played around with a little bit in the last couple of days in class. But the point here now is to make another one and measure the angle between. Okay, so let's see. Let's pick another point on the circle. And let's pull back up the lines we need. We need the side lines. There they are. We'll draw the perpendiculars. Oh, I don't want red though. I want let's see, so we want perpendiculars and we want them in a different color. Let's do blue. So this one in there, this one in there, and this one in here. And then we'll put a couple points down. Point there, oops. I'm going to use the intersect tool. Here it is. Okay. We got our 3 feet of the perpendiculars now. We should be able to get rid of some of the lines we don't want. Some of the perpendicular lines we don't need. And then go ahead and draw in the Simpson line. There it is. And then probably color this one blue, this one blue, this one blue. And then go ahead and I guess measure the angle between them. So if I have an angle measurement tool and I just click on, oops, in a counterclockwise fashion, I get the angle between. Oop. So now I can see that if the two, I guess, poles share the exact same point, they're the same line. But what might be interesting is to measure the angle along the arc. I wonder if you can do that, measure the arc length. I guess one way to do this would be to measure the central angle in between the two lines. So I'm going to go ahead and put the center of the circle in there, and I'm going to measure this angle. And what we should hope to see is that the angle between the two lines is exactly half the arc length of the circle, which is, of course, tied to the central angle of the circle. So just to make it completely clear, the one measured angle should be double what the other measured angle is. And indeed, it seems like it is. The one central angle is measuring the arc length. The angle between the two Simpson lines, of course, is just measured as half that arc length. So that's the proof that we just sketched. And one interesting thing to think about is, well, what does it mean then if the two poles are diametrically opposite? And what that, of course, means then is that the angle of the two Simpson lines will be 90 degrees. And so that's exactly the next little lemma, and that is that if the two Simpson lines have poles which are diametrically opposed, then the two Simpson lines will meet at a 90-degree angle. So again, diametrically opposed. One way to tell when they're diametrically opposed is just to add a segment between the two, and when that segment goes through the center, then we know we're diametrically opposed or darn near to it. And when it's not, then we get something that's going to be less than 90 degrees for the smallest angle in either case, I guess. Yeah. So that's the idea of the theorem that we just proved, and hopefully this makes it come alive a little bit more. It shouldn't be any surprise then that the next lemma is this, that if two Simpson lines for a given triangle are perpendicular, if and only if their poles are at opposite ends of a diameter. And yeah, so that's just what we saw. This proof is just a corollary, right? Because it's easily proved using the previous theorem. Kind of an interesting next place the book goes is here. Given the triangle ABC, suppose that the feet of the perpendiculars from some point Q to the three sides of the triangle are collinear. Then Q must lie on the circumcircle. And hopefully you recognize that this is just the converse, right? Of theorem 3.2. In theorem 3.2, what we did is we said Q, we chose Q on the circumcircle, we constructed its 3 feet of perpendiculars, and we found that surprisingly they were collinear. That's Simpson's theorem, right? So what this shows is that the converse of Simpson's theorem is actually true as well. So it's a biconditional, meaning that it works both directions. Fairly difficult to prove. Your book has a nice proof of it, and I'll let you read that there. But probably the one that I want to do the most on GeoGebra is this one, and it's just a mind blower. If we fix triangle ABC and we let UV be a diameter of its circumcircle, then the Simpson lines of the triangle ABC, having poles U and V, meet on the 9-point circle. This is just fascinating, right? So we choose U and V to be diameters, I guess points that are on opposite ends of a diameter. So we know then that their Simpson lines are going to meet at 90-degree angle. But the point of this is that that intersection meets on the 9-point circle. This really comes alive in GeoGebra, so I thought I would do this one in GeoGebra as well. Okay, so the point here is that we need for this these two to always be a diameter. And so what I'm going to do is I'm going to erase one of them and create it again such that they're always a diameter. So the way to do that, I think the easiest way to do that is just to delete that point and then go ahead and choose a ray here and construct a ray so that we can then construct another point that's diametrically opposed and always remains as such, right? So this will be our new, I guess, pink point, right? And so that new pink point, maybe we'll make it something other than pink because pink looks too close to red. Let's make it a blue point. Okay, so that blue point now, if I move this around, of course, it's going to remain diametrically opposed. And so we should be able to construct its Simpson line fairly quickly and see what happens. So I'll go ahead again, draw in the 3 sidelines of the triangle. We'll construct perpendiculars through here, through here, through here. And then we'll go ahead and place points at the intersections that we need. So these two intersect there. Let's see, these two intersect there, and this one. Oops. Okay, I've got my 3 intersections. I might have actually hit one too many. There we go. Okay, let's go ahead and hide some things now out of our way. We're going to hide the sidelines of the triangle. We're going to hide the perpendiculars. And now we've got our 3, let's see, go ahead and hit line. The 3 lines, the 3 points associated with the foot of the perpendiculars through the blue point. Seems like we should go ahead and color these ones all blue just to keep ourselves clear what they are. Okay, there they are, all 3 blue. Now the thing is that we're not going to be able to move the blue point at all. I'm trying to move it right now, and the reason is it depends on the red point. It's diametrically opposed to the red point, so that means that if I move the red point, then what I get is I move the blue point, right, as a diametrically opposed point. And what you should be paying attention to is the intersection of the red and the blue, because we're told that the intersection lies on the 9-point circle. And indeed, it looks like that intersection is moving in the path of a circle, but how can we know for sure? And one nice way to do this is just to go ahead and intersect the red and the blue line. And we get a point there. And maybe we should, let's see, maybe we should color that point a certain way. I'll pick purple, since red and blue make purple. And then what's really cool in GeoGebra is that now you can go ahead and watch that purple line, but even more so, what's really fun, purple point, is to go ahead and choose the scroll wheel at the top and show trace. So this is a perfect example of a place where tracing helps. Now the purple point will be traced in its path wherever I move. Now it gets a little bit messy because, for example, right now what I could do is I could adjust the triangle and then the purple point will do something different, but it still seems to be a circle, right? You getting the idea here? So sometimes it's helpful to erase the traces. You can find that over here under View, Refresh Views, and it'll erase traces, and then you can, adjust the triangle however you want. Unfortunately, the traces go with you, even if you're adjusting the triangle. So I'll go to Refresh Views again and just march my, refresh views and march this red point around. And again, it does appear like that could possibly be the 9-point circle. Remember, the 9-point circle includes the midpoints of sides, and it does seem to be intersecting the triangle at midpoints of sides, at least on the left side and the bottom side. The right side, we have both midpoint of side and the foot of the altitude. Even neater than trace, though, in my opinion. I'll go ahead and refresh views here quickly. So here's our purple point. I'm going to turn the trace off, so I'll go turn the trace off, hide the object properties. And so now I'm back to just the picture untraced. But anytime a point is restricted or controlled by another point, you can look at the locus of all the points that it's going to construct. And the locus tool is actually located, under the perpendicular drop down. It's the last one, locus, and you can read the instructions. It says select locus point, then point on object or slider. So the point we want to construct the locus of is the purple point, and the thing that controls it is the red point. So I'm going to select the red point now, and it shows me the locus, that is all the places the purple point can go. So I'll go ahead and do it in purple, and now you can see that this is the path for that particular triangle ABC that the purple point will trace. And the purple point, again, is just the intersection of the two Simpson lines, which are perpendicular because their poles are diametrically opposed. Wow, isn't that a mouthful? But what's really neat about this is that you don't have to erase traces. You can change the shape of the triangle, and the locus will update, and we can see the relationship then between the purple and the black and the triangle. And here's a nice example where we have an acute triangle ABC, and I guess the two Simpson lines associated with red and blue going around the circumcircle, diametrically opposed, and of course their intersection tracing out the 9-point circle. I don't know if that doesn't blow your mind. I don't know what will. It just seemed quite elegant to me when I first saw it, and I thought it would be worth sharing today. Okay, well that's really all I wanted to go through for the rest of this chapter. Just an amazing fact, and I'll follow this video up with another video on chapter 3B, and I look forward to getting back to class on Monday. See you all then.